So the floor is yours.
All right, good afternoon, everyone. My name is Wojciech, and this is my team, Marcella, Brendan, Jonathan, Ali, and Anastasia. Our product is called the Autonomous Precision Pipetter, or app. This presentation is going to demonstrate key components, design changes, and analyses that show the effectiveness of the app.
So this video is going to show a quick demonstration of how the product works. The volume range we were required to meet was 10 to 200 microliters. In this demonstration, our target was 169 microliters, which is equivalent to 169 milligrams. And as you can see, the mass that we were able to reach was 169.1 milligrams. So we did stay within the error requirement, which was plus or minus 1 milligram.
All right, so next up, this short video is going to demonstrate the key components of the app. To start off, the 3D printed exterior casing and top plate and the aluminum base plate shown fully encase all of the dynamic components of the app. The app connects to the gantry through the magnetic plate at the front of the casing that is shown right now. After removing the exterior casing, the interior casing and components are revealed, and I'm going to let that play out for you guys right now. All right, so the app uses one limit switch to prevent the interior drive nut from over-ascending within the casing, which could cause system failure or material damage. The inner components you see easily separate into two sub-assemblies by the removal of 4 screws from the bottom of the base plate as shown. Now on the bottom subassembly, we have the pipette and ejector mechanisms. The 10 to 200 microliter pipette tip that we are working with press fits onto the pipette. 2 spring-loaded shoulder bolts screw into heat inserts found within the U-shaped ejector. And finally, the aluminum pipette is threaded at the top to screw into the aluminum base plate. And 2 O-rings are placed within the pipette to create the seal. Next, on to the top subassembly, which includes the NEMA 17 motor, lead screw, drive nut, and plunger, all located within the interior casing. The plunger is secured to the drive nut using a set screw, and of course, the lead screw is screwed directly into the drive nut. And this concludes all of the components of the app.
So here we're going to show how the tip is ejected off the pipette. This design uses shoulder bolts that were fastened to the U-shaped ejector using heat inserts. So as the drive nut moves downward, it pushes down on both shoulder bolts and the ejector pushes the tip off. When it moves back up, the springs decompress, which bring the ejector back up to the final position, to the initial position, sorry.
All right, so I'm going to talk about the evolution of design for app. So first, for the pipette ejector system, originally first drawn on paper, shown in the top right, the ejector was just the sock over this nozzle, and we just called it the toilet seat, instead of the final U-shaped piece that we ended with. And the first idea included some sort of elastic lining at the top of the nozzle where the lead screw enters, and as it moves the plunger down past that final position where all the fluid is dispensed, the drive nut will compress the elastic material to slightly move the ejector past the final position of all the fluid ejected to just push the tip off. So this turned out to require way too much precision in thinking. And the idea and function was there, but as the drawn picture shows, mechanically it doesn't really make sense. So therefore we replaced it with springs, which allows for much more visible compression and simpler configuration. Also, the U-shaped piece used to be an L shape. Then a simple realization came up that the system would last longer if the force was balanced when compressed, as a one-sided force on a non-symmetrical piece would cause problems. Because of the springs, the U-shaped piece is made of PETG along with the other plastic parts, since only small forces are applied to the piece, making any sort of metal a bit overkill. And for the nozzle design, in order to prevent the leaks, the first design included a nozzle with just a single female gland, which is shown in the bottom right, to hold an O-ring that the plunger would slide into. With initial testing of the project, the nozzle tip leaked a bit when the pipette was full of fluid, so we concluded that the underlying issue was the nozzle not being fully sealed. Therefore, we just added another female gland in order to put another O-ring inside, and after testing the dual female glands, there were 0 leaks when the pipette was full of liquid, making the nozzle fully sealed. So for the base plate design that would connect the nozzle and ejector to the chassis, originally the base plate was printed with the outer chassis as just one piece. With this design, assembly and disassembly was like well over 5 minutes of the maximum time. Therefore, the base plate was just moved to be an entire part itself, shown in the bottom left, that allowed for easy assembly. With this design, the assembly time was greatly reduced to 4 minutes and 30 seconds. And the part was also made of aluminum instead of PETG material, as the aluminum nozzle had to be screwed into this base plate. And if the base plate was PETG, then the aluminum threads of the nozzle would just break the threads of the base plate.
Before we started manufacturing, we needed to ensure that our design could reach the required tolerance. And this was determined by 3 main factors. One being the radius of the plunger, which we chose to be 3 millimeters, the lead of the lead screw, which the pitch was 2 and had 2 starts coming to a lead of 4 millimeters, and the minimum step of the stepper motor, which was 1.8 degrees. The smallest height change is calculated by converting the lead of the lead screw to height per degree rotation, and then multiplying it by the step angle of the motor, which came up to a distance of 0.02 millimeters per step. Then this is input into the as the height into the volume calculation, and using the volume of a cylinder along with the radius of our plunger, this produces a minimum volume achievable of 0.565 microliters, which is smaller than our required 1 microliter. The last thing we needed to do was determine how high we needed to raise the plunger in order to reach our minimum and maximum volumes. Our minimum was 10 microliters, our maximum was 200 microliters. In order to do this, you simply divide the volume required by the minimum volume achievable times the minimum height achievable by the stepper motor, and it brings you to a height required of 0.35 millimeters for the 10 microliters and 7.07 millimeters for the 200 microliter.
For the failure analysis section, we wanted to ensure that 2 main things will be able to work within the app. First, we wanted to ensure that the O-rings will be able to last. It is known that O-rings may fail due to nibbling and extrusion, which may happen due to high stresses. Thus, the stress per O-ring was found by finding normal force on the O-ring, which occurs from the sides of the nozzle over the exposed outer area of the O-ring. The normal force was found by using the outer area of the size 9 O-ring as well as a friction coefficient. The stress was found to be 0.8 megapascals per O-ring. Each O-ring will thus last more than 18 months according to the time-variant reliability analysis for rubber O-rings from the NCBI. Next, we did the failure analysis between the drive nut and the lead screw to ensure that the plastic drive nut would not fail due to shear stress. The shear area of the internal threads was found. That was used to find the linear force that gets applied onto the threads. Finally, the shear force was found as a linear force over the area of contact between the screw and the drive nut. It was found as 3.01 megapascals. The shear stress of PLA plastic was found to be 33 megapascals, so the inner threads of the drive nut will not fail.
Now it comes to testing. So to work on testing, the pipette was assembled as shown in the previous slides, and the limit switch was connected to it. Then it was wired to the apparatus in the lab, and as shown in the left picture, and connected to the Arduino board shown in the right picture to be able to give various degrees of rotation to the lead screw, which corresponds to specific volumes. The various aspects of testing included several points. Number 1 was that making sure that there is no leak in the pipette and that it can hold all the liquid with no issues of interference between the drive nut and the outer and the inner casing of the pipette. Gain a calibration curve that relates between our degree of rotation of the lead screw and different volumes. This is the calibration curve that was obtained, where X is the volume that is being asked for, and Y is the corresponding degree of rotation needed. The degree of rotation that was needed to get the max volume of 200 microliters was 687 degrees. That value was divided by 200 as shown to get the degree per microliter. which is then used to multiply by the desired volume to get a predicted degree of rotation for the specific volume. So for example, if we want to obtain 175 microliters volume, we get 601 degrees plugged into the Arduino code. Number 3 is that an experimental table of values was obtained to get the calibration curve that was shown previously. And finally, the accuracy of the pipette was observed to be within allowable limits as the volumes are relatively high and it can be higher in lower volumes. The limit switch went through the testing of accurate placement where the drive nut will hit the sensor to locate a maximum displacement that the system will not exceed. That helps to assign a point of reference. Finally, to wrap up, the deliverables of this project was to create an automatic pipette as a part of a bioreactor that can hold and dispose liquids within the intervals of 10 to 200 microliters with an accuracy of 1 microliter. App went through various iterations of designs and testing to get a device that reaches the design requirements and can be approved. After doing many iterations of testing in lab, our group concluded that the overall technology readiness level, TRL, of the project is level 4, which is that the device was validated to work in lab. Thank you so much for coming and joining us today, and we are happy to answer any questions that regarding our design. Thank you.
Fantastic, guys. Thank you very much.
Thank you.
So we'll go ahead and open it up for members of the panel to go ahead and ask you guys some questions.
So this is Rick Miles from Northrop Grumman. So one of the things you jumped right into talking about your pipette. I would have liked to have seen kind of an intro up front that kind of told me why you were going about doing this. Just jumping in, I felt a little lost at first and kind of had to catch myself up. I mean, I know I've seen several of these presentations, but I just think it would be useful. Always make sure you educate your audience as to why you're going about doing the particular project before leaping into talking about it, okay? I also thought it was interesting because you seem to be the first group that really is concentrating on making a lot of your materials out of aluminum. But one thing I didn't see, because a lot of the others are doing 3D printed material, I'm wondering if you did a cost analysis or what drove that decision.
So
go ahead.
Well, to answer the part of that question was what drove that decision to use aluminum. We definitely focused as much as we could to do the 3D printed materials. It was easily accessible in our lab, but for certain things such as the base plate that the pipette, which is also aluminum, had to be threaded into, that had to be aluminum to match the threads. Those are the two main things, because the ejector itself, that U ejector, was 3D printed. The casings were 3D printed, and the top plate also was 3D printed because it didn't have anything screwing into it. So those are the main two or three things that were aluminum.
Okay.
Yes.
So can you go back to the overall picture of your so not there. Go on a couple more. Yeah, so I guess maybe here, when you played the video, it wasn't clear to me, I guess, as to what was aluminum and what was 3D printed. It all looks like shiny metal to me.
Right. That definitely is not clear by just looking at the footage. During my part where I was talking here, I tried to emphasize it because I mentioned the exterior casing and top plate were 3D printed, and the bottom plate, which you can't see here, but later on the video, is aluminum, right, which is what the pipette threads into. Oh, there
Yeah,
you go.
I
So,
guess as I was looking at things there, right, I really tagged on to the fact that you had the aluminum the pipette, and so I guess I started thinking the whole thing was made out of aluminum. So
yeah. So again, yeah, just to break it down again, the only things that are actually made of aluminum is the bottom base plate. If you could zoom into that, Jonathan, that right there, the pipette itself, and the drive nut, which is inside. So we can't see that right now.
Drive nut's still plastic.
Oh, okay. Sorry.
you
I
mean
think
the
what I
plunger.
meant to say was the plunger. Yeah, that was my bad saying.
all right.
I tossed in the comment in chat to make sure that you set your materials in CAD correctly. I don't know if they are or not, but this is a huge thing to make sure that you got your materials set properly. And then also for something like this, material appearance also matters. I think that would have alleviated a lot of the confusion. If you
Absolutely.
make the outside casing black or blue or something.
For sure.
Yeah, that was a color thing. Yeah.
Guys, this is Tom Singer from Northrop Grumman, and I apologize coming into the presentation 90% of the way through, but I'll kind of follow on Rick's question. If you got a bottom plate that you're saying is going to be made out of aluminum, why are we making a top plate why are we 3D printing a top plate?
So the top plate is basically just to seal it from the top. From the top, it doesn't have any functionality other than that. But the bottom plate needs to be screwed. It would be screwed into this pipette that Jonathan is highlighting. And when we
Okay, so you're
when we
threading
did
that?
that as
Yes.
so there are threads in here. When we had it as a
Okay.
3D printed part at the beginning, it didn't actually work, and it was breaking very easily. So we had to put that in aluminum. But yes.
How hard is it to make a flat piece of aluminum with looks like 4 holes in the top of it versus the time it takes to 3D print something like that? And what are the trade-offs in material in terms of cost, in terms of any sort of compatibility issues?
So we 3D printed the top part because as Wojtek mentioned at the beginning, is that 3D printing was very accessible in our lab. So we just tested it. We just printed it in one night and just use it in the next day. But yeah, I can understand your point that it could have been easier if it was 3D, if it was aluminum. But we will need to actually do more testing to see if it can hold the weight of the aluminum on the top. But yes.
Yeah, I would suggest that's not very heavy. I wouldn't expect that to be a concern. But I mean, ultimately, we're designing a product to be produced, right? Not a product to be prototyped.
Mm-hmm.
So I would, sort of consider those sorts of things as you're designing and building. And certainly, if you're putting together a prototype and checking functionality, that's an opportunity to maybe do something with 3D print because it's just more convenient for a one-off item. But I don't believe that's really the goal here for this design.
Yeah.
We have any more questions, comments? Otherwise, Dr. Traum and I get to jump in. Oh,
I'd have more, but I was only here for like that last 10%.
if you're only here for 10%, you got more questions. That means it's a good sign, I think. I did want to pipe in just real quickly and say that I did really like that you had the video showing everything at the beginning. I can understand the confusion with everything being shiny.
Yes.
But it was actually, I think you're the first group I've seen at least, to have a full tear down of what all the components are and go through it piece by piece dynamically, which I personally am a fan of.
Me too.
Thank you.
I'm sorry I missed that.
It was good, Tom.
Oh, here it is.
Yeah, I know Tom also appreciates the fact that nobody's been doing FEM this semester.
We learned from
Yeah,
last
buddy.
semester. Now that you've mentioned it, the color is very difficult to tell what's metal and what's not. That's a good point.
How's that piece that just came off attached?
Oh, that's actually a mount. I'll take that one because that's not something they had to design. That's going to be mounted to the wall inside the enclosure, and it's just a it's almost like a dovetail type joint.
So it just
think like a,
you hang this up when you're not transferring fluid?
So you have to hold it up on the wall of the enclosure when it's not in use.
Oh, okay.
So think like a French cleat.
Yeah.
And so it's that type of a device on the wall. So you can have multiple tools to the XYZ will move over and grab tools as required.
And this is just one of those tools.
Yep. This is just one of the tools.
Very cool.
So
okay.
With the whole, because we got a couple of minutes here with the presentation with this design, there's the 3 different volume ranges that we targeted, and that's because there's going to be one pipetter of each volume range in the final device.
Okay. I got you. Okay, so I'll say I was somewhat confused by that. I thought I've seen this little like triangular shape on everything, and I assumed that the idea was to use the pipetter to pick up a tool on the outside of the pipetter, right? So like the ODFI kind of tool that would be attached to the pipetter, but that's actually where that's attaching to the XYZ system.
So there's the little. Can you guys get a rotation on where we can see the tool plate? Because this is.
Do we have that, Wojtek? Or is that something you edited in post?
Oh, it's right there.
Yeah, right there.
Oh, yeah.
So no, other side. That tool plate right there is a kinematic mount.
Okay.
It's actually a scaled down. Fran is in the talk right now, so it's actually a scaled down version of what Fran's group worked on last semester in Mech 3 over the spring, the tool changers. And so we scaled one of those down. So this little bit, orange is a terrible color in Zoom. This little guy right here there's a magnet that sits in that internal boss right there that I just darkened up. And then ball bearings sit in each of the 3 other holes. And so it's a kinematic mount. And that's what attaches to XYZ. This plate on the back is on the wall of the enclosure and is what acts as a tool holder for almost like the carousel in a CNC machine.
Okay. Man, so this changes everything, man. This is why I've noted in a couple of the notes I've been writing down for the teams, like show what your interfaces are. And this is maybe, a combination of me being unfamiliar with the overall design and them being too familiar with the overall design that I don't think anybody's really explained that aspect of their systems. No,
that's actually, I think I'm actually really happy you guys finished a bit early because this is a fantastic discussion to be having right now. Because, I think anybody once you get really deep into a project, you start losing sight of the periphery of it. I know if somebody asked me about my PhD research, like it's pretty much a whoosh. But it's because I did it for 6 years. So I don't even think about the things that are common knowledge for the field. But, Archard's wear law is not common knowledge. I think even for structures guys, you're familiar with wear, but you might not know the details of that, outside of the realm. If you're a tribologist, you know it. And I would just immediately start going and deriving things from that and explaining it and jump over all the foundations. And I think that's a really good thing to be aware of for you guys for the next time, if you're giving a product demonstration, always remember, hey, we know all this stuff, but sometimes our audience doesn't. And it's always good to have that touch point of like, this part's going to attach to this thing and this part's going to attach to the other thing. But
yeah, that makes a lot of sense. I think we kind of went in thinking that because everyone's presenting basically the same idea, we thought it would be known. But yeah, you're right. Either way, we should be introducing it more in detail, exactly what the goal of the task is.
I think everybody went into it with the same idea you guys had, and we're now, 2/3 of the way through, 3/4 of the way through, really, 7/8 of the way through, and it's like, oh, oops. So now that that's been clarified a little bit, we still got a couple of minutes. Tom, you said you had some more questions.
Well, I was looking at that back plate, but it sounds like that the plate that would be attached to the wall isn't necessarily part of their system. But I'm looking at what look like countersunk holes that are fairly deep. Probably not a major issue, but when you start countersinking thin plates, you wind up creating very, very thin pieces of structure, which, again, probably not an issue. It's never really going to be loaded, but that's what we refer to as a knife edge condition, and that's a really common place for cracks to initiate. Again, not, something like this, it's going to be very lightly loaded, maybe not such a big deal, but I don't know. I see that and I flinch a little bit.
Yeah, I think it's got the counter bores on the back are for rivet nuts to give clearance around the heads of rivet nuts. And then the countersink is so it's flush, so if their tools were wider, they wouldn't interfere.
Yeah.
Oh, that's a null design part. Don't hold it against the students.
Yeah, no, I'm not.
Rick, did you have any last parting comments or questions?
No, I think they answered all my questions. I thought it was again, all these designs are a little different, and I like the different approach taken here.
All righty, excellent. Well, we'll go ahead then finish up. So congrats, guys. You're done. You're free. Well, except for the final report stuff, but congratulations. Job well done. Thanks for helping. Thanks in particular for helping to seed a great discussion.